Hello everybody, welcome to the practical exercises part of the pair formation model lecture. Okay, exercise number 1. Given the system of ordinary differential equations which describes the evolution of the pair formation process in a population with background demographic processes, prove that if the system starts in a state where total initial population adds up to b over mu, prove that the system the total population size will remain in the same state for the all future times. Here is a solution to the exercise 1. So first set n of t, the total population size, to be equal to x of t plus 2 times p of t. So that would be the variable that captures that. And observe that the differential operator can be distributed over sum. In other words, n prime of t, the derivative of n with respect to time, equals to x prime of t plus 2 times p prime of t. And therefore, if we want to find the derivative of n with respect to time, what we really need to do is add the derivative for x of t, which is given as the first equation of the system, plus twice the derivative of p of t. Once you write all the terms of both equations, and not forgetting to multiply the p prime derivative by 2, we can combine some terms. So b doesn't have a pair and gets copied as it is. We can combine terms that contain death rate mu, like so. So minus mu times x plus 2p. And we see that the remainder of terms such as rho x will get cancelled out. And so what we end up with is n prime of t is equals to b minus mu times x plus 2p, which of course we recognize as the expression for n of t. So in other words, n prime of t equals to b minus mu times n. Let's find equilibria of this equation by setting the right hand side of the equation for n prime of t to 0 and solving for n. And so what we're seeing is that this equation n prime of t equals to b minus mu n has an equilibrium equals to b over mu. We of course know that if we have started in this state, then we will end up in the state for all future times. And therefore, the conclusion holds. Exercise number 2. Given this system, which once again describes the evolution of the pair formation process in the population with the background dynamics, such that the initial conditions for the system, for the initial size of the system is given by this equation, we ask, at an equilibrium, what is the fraction of the population that is single? Now, to find an equilibrium of the system, what we need to do is to set its right hand side to 0. So in other words, we're setting x prime and p prime to 0 and solve respectively for x and p. As we solve this system of equations, we will need to use the following condition: x star plus 2p star equals b over mu. Now this is true because of what we've proven in the first exercise. If we have started from the total population size of b over mu, we will remain in that population size forever. Now once we evaluate the system and solve it for x and p to obtain x star and p star, we arrive at this expression for x star in terms of the birth rate, death rate, formation rate, and dissolution rate. Now, since we are asked about the fraction of the population that is single, we will need to divide capital X star by the total population size, which of course we have just shown will be b over mu. And so the fraction of the population that will be single at an equilibrium is given by the following equation. Exercise number 3. Given the following system that describes coupling of the pair formation process with the disease dynamics, convince yourself that the system essentially describes the same pair formation process as seen on the preceding slides. In order to do so, you define two new variables. You define x of t, which pretty much tracks the number of single individuals in times and is equal to the sum of xs and xi of t. And defined p of t, which is equal to the sum of pss, psi, and pii of t. Of course, note that the differential operator can be distributed over the sum, and therefore if you would like to find the derivative of x with respect to time or p with respect to time, what you really need to do is adapt the derivatives of compartments xs and xi respectively, or pss, psi, and pii respectively. So let's start with the singles compartment. So x prime of t equals to the sum of derivatives of x of s and xy. Copying the terms from the definition of equations, including both relationship formation terms and disease transmission dynamics, canceling some terms, collecting the terms with the same parameter, we arrive on the following: x prime of t equals to minus rho times xs plus xi plus sigma 2pss plus 2psi plus 2pii, which we of course recognize the first bracket as xs plus xi is equals to x of t, while the second bracket is p of t multiplied by 2. And so we say that if x of t is defined in this way, then its derivative, according to the definitions given on the previous slide, is equals to minus rho x plus 2 sigma p. Well, if you go back and look at the pure pair formation process, this is exactly the equation that describes the evolution of the single individuals in the population. Now let's deal in a similar way with pair process in the population. So in order to describe the derivative of the total number of pairs in the population, we will need to adapt individual derivatives with different types of partners. So we're copying both the terms that represent the pair formation process as well as disease dynamics process. Now we collect the terms with the same type of the parameters color coded here. We cancel what we can in the remainder, and we arrive at the following expression: 1 over 2 rho times the sum of permutations of single compartments divided by the total sum of the single individuals minus sigma times pss plus psi and pii. So the second bracket is of course very easy since we recognize this as a definition for p. While the very first bracket, if you will look at this closely, you will see that the numerator is equal to the sum of xs plus xi squared, and therefore we can divide numerator and denominator by xs plus xi such that the whole fraction is actually equals to xs plus xi, which of course we recognize as a definition for x of t. And so what we arrive at is that p prime equals to 1/2 times rho times x minus sigma times p, which corresponds to the definition of the differential equation given for the number of pairs in the population. And therefore the full system that couples disease dynamics with the pair formation process can be reduced as pure pair formation process. Thank you very much for your attention.